Hi, good morning. Hope you're all doing fine. Today I'm here with another topic, which is voltage source inverter. Yeah. What is voltage source inverter? It is one of the power electronic converters, right? So how many types of power electronic converters we have? We have 5 different types of power electronic converters. One is AC to DC called rectifiers. The second one is DC to DC choppers, which is like choppers. And third one is DC to AC converters, which are called inverters. And fourth one and fifth one are same AC to AC converters. If you differentiate fourth and fifth, the fourth one is about AC to AC converter with a voltage variability and fixed frequency. They are called with the name voltage regulators. And coming to the fifth one, it is about AC to AC converters again, but fixed voltage and variable frequency in its output. So this is called cyclo converter. So likewise, you have about 5 different converters. It's very easy to remember. If you stretch forth your palm, you'll find 5 fingers, right? 1, 2, 3, 4. And then we can 5, and then we can even classify your converters AC to DC, DC to DC, DC to AC, and AC to AC with voltage variable and fixed frequency. And the fifth one, the last one, is AC to AC converter with fixed voltage and variable frequency, which is nothing but called as cyclo converter. Today in this lecture, I'm going to make some discussion on voltage source inverter. From the name itself, you can understand it's a one which converts a voltage from its DC form to AC form. Very simple. From a unidirectional voltage waveform will be converted into bidirectional voltage waveform. Very simple, right? So even we use it in the countries where we find, in the places where you find power outages are very frequent, so we definitely use this inverter so that we can have a continuous power supply. That's called, that's used in our UPS, uninterruptible power supplies. That's okay. That's about a general introduction about the converters, which is called inverter. And coming to this specific type, voltage source inverter, this is about a 3-phase voltage source inverter, which is going to convert DC voltage into 3-phase AC voltage. Very simple. DC voltage is to be taken from a battery and give it to the configuration of the converter, which is voltage source inverter, and thereby by having a proper switching action, you can get a 3-phase output voltage. 3-phase output voltage is very simple, right? You can have phase A, phase B, and phase C. Very easy to understand, but it's not going to be a simple discussion. It's going to be a lengthy discussion. I would expect you to pay a little more attention towards this topic, right? And in all the textbooks, if you can see, you will find that the discussions are more than, will be about more than 3 to 4 pages, if I'm not wrong. So let me go ahead with the circuit diagram, how it is going to be, right? Yeah, see, this is your supply battery, right? And then we're connecting a switch here. I'm going to explain it, spend some time on this switch. What is this switch all about? And yeah, so there are 3 legs in this converter, which is called inverter, right? Fine. And yes, this is the supply voltage VDC, and now this is the output that we have. And see, this is 3 phases that we have it: VAN, VBN, and VCN. Am I right, my dear? That's okay. So yeah, let me name this all switches, right? This is a switch. The dotted portion, what I'm indicating, is a switch. What switch is it, sir? The question arises there, right? What switch is it, sir? It's a power semiconductor switch. What is it? It's a power semiconductor switch. So what is power semiconductor switch? Power semiconductor switch. Okay, so power semiconductor switches starts from diode, right? So you have diode, diac, thyristor, triac, transistor, MOSFET, IGBT, BJT, many GTO, MCT, many types of power semiconductor devices are there. These are called even power semiconductor switches, right? So when I'm calling this as a switch, it is not a mechanical or an electrical switch that we find in our daily life. It's about power semiconductor switch, which is nothing but a diode. So but we're not going to use a diode here. We're going to use two different families. One is called transistor family, right? And the other is thyristor family. So power semiconductor devices, as far as this power electronics is concerned, it is divided into two different types. One is transistor family, the other is thyristor family. So if you can see, in transistor family, you find first one BJT and then power BJT, right? Power BJT for high power applications, and you'll find MOSFET, right? And then you find IGBT, right? These are all the different transistors that are available in the family of transistors, which are referred to power semiconductor switches. Now let us see thyristors. Thyristors starts from SCR, basic SCR, the same is called thyristor, and then you'll find a GTO and then MCT and so on. So you'll find many different power semiconductor switches. If you can see a book called P.S. Bimra, which is on power electronics, in the first chapter of the book, right? You'll find, in the first initial chapter, you'll find a biggest list of all the available power semiconductor switch, right? So right, this is about the different power semiconductor switches we're going to use in this, right? You can use thyristors or you can use transistors, but I'm going to use a transistor here. The reason is thyristor family or thyristor based or thyristor switch power semiconductor device, which is under thyristor family, has got a limitation. The limitation is like this. The limitation of it is it has a problem or a kind of limitation in terms of its commutation. So if you wanted to turn off a ACR or turn off a thyristor, definitely you have to take a auxiliary thyristor called auxiliary circuitry called commutation circuits, right? You would have, we would have even seen in our power electronic course, maybe in the first introduction chapters, you find commutation circuits or commutation circuit class A, B, C, D, E, 5 different commutation circuits we see, and we may have to use all that commutation circuits to turn it off. The reason why we need to turn it off, because the supply is always DC. You can't turn off a thyristor unless and until you have a negative half cycle in the supply itself. What is it? If you wanted to turn off a thyristor, you should reduce the current less than the holding current. There is no doubt in that. At the same time, you must even have to have a reverse biasing voltage from the supply end. What is reverse biasing voltage? Nothing but a negative voltage from the supply end. But here in a DC to AC converter discussion, you find DC supply, battery as an input, right? So when you have a battery input, you would find the battery voltage continuous with respect to time. It doesn't get to zero at any point of time. So there is no possibility of having a negative voltage or a zero voltage in the supply. By means or based on that, what you can draw from it. So because the supply is not going to negative, because the supply is not getting to zero value, we can never turn off a ACR with the actual arrangement as it is. So what you need to take additional arrangement, or you need to take an auxiliary circuit, and that auxiliary circuits are called with the name commutation circuits. The meaning of commutation is changeover from on to off and off to on. This is how you have a commutation circuit requirement in the case when you use a power semiconductor device under the family thyristor. So it's not going to be so suggested to use this family devices when you are taking a inverter discussion. So I take a transistor. Why, sir? Why are you considering transistor? The reason why I take transistor is it is very simple to turn it on as well turn it off. It depends on the gate pulse or a base current. If I make base current high for a bijunctional transistor, I can turn it on provided there is a VCC connected to it. So if I want to turn on a transistor, I need to give a base current, let's say 1 ampere. If I give 1 ampere to the base current, provided a VCC is connected to the transistor will be on. And as long as you wanted to keep this transistor on, you can keep this base pulse, base current on. If you give a train pulse, I mean a continuous pulse to gate current, that would keep the transistor on as long as this IB is flowing into the base of the transistor. If you make this IB 0, then the transistor is going to be turned off. I hope you are getting me. So commutation, I mean switching off of transistor is not a big deal. By just making this IB 0, you can turn off the transistor. It's very easy, right? So commutation, this commutation what you find here, our turn off process, what is involved in the transistor is very simple. Apply the gate pulse wherever you want to turn it on, and then the switch is going to be on. And if you wanted to keep it on for about 10 milliseconds, or you can translate that into degrees, 180 degrees, you can keep that IB continuously given to that base of the transistor until 180 degrees or until 10 milliseconds. And at 10 milliseconds, if you wanted to turn it off, make this IB 0. I mean, give a 0 amperes to the base, and thereby it's going to be turned off. Something like, it depends on the gate pulse what you provide. So if you are giving a gate pulse high, let's say 1 milliampere, the transistor is going to be on. If not, it's going to be off. It's not the case here, my dear. You can turn it on with an impulse, but turning off is going to be very tough. You need to have a commutation circuit. That's the reason why we are considering only transistor family, to make the discussion simpler and to have a self-commutation. This process of commutation is called with the name technically self-commutation. Hope this is a discussion that this is information about the power semiconductor switch. Now coming to the converter and its discussion. So how many switches are being indicated? Now see, the switches that are indicated are S1, S3, S5, S4, S6 and S2. What is this numbering? Is it like randomly I picked up, or is there any specific reason for taking this particular numbering? Yeah, there is a specific reason. To keep the switching sequence consistent in a sequence, in a descending order, you have to descending or ascending order, you have to make this numbering as it is, 1, 3, 5 and 4, 6, 2. For our notation, we can understand like all odd numbered switches are on the top and all even numbered switches are at the bottom, right? Are you with me? Yes. So hope you are understanding what is a switch and what is the names or numbering that is given to it. For our understanding, if I have to make a blind notation here, I'll do like this, So how to remember it? So 1 and 4, okay? Suppose by chance you may confuse in the examinations and you may write it up with 1 and 5. So how to avoid it? Or 1 and 6 here. So instead of taking 4, 6, 2, you may take 6, 4, 2. So how is the point of a blind notation to understand this particular aspect? So I would understand like this. See, if I subtract 4 from 1, I would get 3. If I subtract 6 and 3, I would get 3. If I subtract 5 and 2, I mean 5 from and 2 from 5, again I'll get 3. So there is a difference of 3 in this numbering, right? Why? Because it's a 3-phase converter. So in a 3-phase converter or an inverter, if you wanted to number the switches, you have to follow that the difference should be 3, 1, 4, 3, 6, 5, 2. This is how I would take the numbering, right? And coming to additional discussion that I can give before I go to the working principle, there are 3 different legs. How many legs? Leg number 1, leg number 2 and leg number 3. So each leg is connected to each phase, its respective phase. So let's say number 1, first leg, which is comprising of switch number 1 and 4, is connected to, is considered, its output is considered as phase A, and it is second leg is connected or given or taken out as VBN, okay, and this is VCN. That's fine, right? Now, I'm going to make some idea on how will be the output voltages that we are expecting here. So the output voltage is what you have seen here. This all output voltages has got a phase angle, right? Phase angle. So 0 degrees, 120 degrees and 240 degrees. So VAN will start at 0 degrees and VBN will start with a delay of 120 degrees. If you convert that in time for a 50 hertz output voltage, what do you want? 120 degrees is more or less equal to 6.667 millisecond. And coming to this 240, VCN will start its journey. It starts with a delay of 240 degrees. You can convert that into its equivalent 10 millisecond, time also in terms of millisecond. That's fine. So VAN, VBN, VCN are the output, expected output voltages which are starting at different angles. Definitely there should be a 120 degrees difference, and phase A will start at 0, and then phase B will start with an angle of 120 and phase C will start with an angle of 240. So I am assuming that you have all this prior knowledge before I proceed to the next discussion. If you don't have, please get back to your basics, right? So VAN, VBN, VCN, what is the phasor diagram and what is the angle that I am referring here. So coming to the operation or working principle of it, how I can get output voltages from the available input. Very simple. How I'm going to get the output voltages from the available input. So how many output voltages you have? 3. And how many inputs you have? Only 1. Something like you are sharing some food from 1 person to 3 persons, right? There is only one, let's say 100 volts is the input. So how much would be to each phase? Very simple. You can say that it is VAN, VBN, VCN will share 30 percentage, or 33. So that it's going to be 100% of the supply. Is it okay, my dear? So you're with me, right? So VAN, VBN, VCN will share this voltage with an equal proportion. Definitely it's going to be it's going to be seen when I draw or plot the waveforms here. Now what about VAN? How can you get VAN? How can you fabricate VAN? You can fabricate VAN with S1 and S2, S4 alternatively turned on and off. Okay, something like this. VAN can be fabricated by switching on 1 and 4 switches alternatively. If you wanted to have phase positive half cycle of phase VA, then you have to turn on S1. Hope you are with me, my dear. Listen to this very carefully. And if you wanted to have a negative phase A voltage, then you have to turn on S4 because it is connected to the negative of battery. What is it? To turn on, to have positive half cycle of VA, you have to turn on S1. To have negative half cycle of VA, you have to turn on S4, right? And then if you wanted to turn on B, if you wanted to fabricate B, it is to be done, or it can be done with a second leg. So second leg is meant to fabricate phase B. First leg is meant to fabricate phase A. Third leg is there to fabricate phase C. Okay, so how to get phase B? If you wanted to get positive half cycle of phase B, then turn on S3. And if you wanted to get negative half cycle of phase B, turn on S6. Okay, if you wanted to get positive half cycle of phase C, turn on S5 and negative S2. Hope you are with me, right? So turn on means you have to apply a triggering pulse. Very simple, I said here, right? You have to apply a base current to the transistors which are present there. So when I apply a base current, is going to be turning on the switch. So I'm going to turn this on, turn this S1 and S4 or S1 to S6 in a sequence which is called switching sequence, so that I can fabricate all 3 voltage waveforms in my output. Okay, hope you are going with me, right? So now I have a some question for you. What happens if you turn on S1 and S4? What happens if you turn on S1 and S4? So definitely if you turn on this and this current is going to be circulating, looping here itself. It's something like you have some sump in your building, right? And if all the taps are open in the first floor itself, in the ground floor itself, no water reaches to the top floor. Okay, this is the top floor and this is the ground floor. So if all are closed, so water will loop there itself, right? If there is some problem with the pipeline, so water will loop here itself. Water doesn't go this way. It is simply like the flow of water, right? So the flow of voltage from one end to the other end through these switches is nothing but closing the taps. If you close this tap and this tap, alternatively manage it, you can get the output voltage. So you're understanding me, right? Closing the switch is nothing but turning on the top tap, and opening the switch is nothing but turning off the tap. Thereby you can control the flow of water, nothing but flow of voltage in the output. Hope you're with me, right? Yeah, I have some more points to put on in front of you. So what will be the on time of S1? What will be the on time of S4? On time of S1 doesn't depend on anything else. It depends on only Van, positive half cycle. So how long you wanted to keep a positive half cycle? Usually if you wanted to have a constant output voltage, you would expect the output voltage Van to be stretching for about 10 milliseconds if you are expecting a 50 hertz waveform, 10 milliseconds. So keep a base current stretching from 0 milliseconds to 10 milliseconds for this. That is called gate pulse, so that you can turn on S1 and then you can get a output positive phase A voltage, right? And at 10 milliseconds, let's say at 180 degrees in terms of degrees, right? You turn off this S1 and turn on this S4. Thereby you can get a negative half cycle of phase A, right? And how long that this should be on? It should be on from 180 to 360, because the second half cycle, which is called negative half cycle of phase B, will be stretching from 180 to 360 in terms of seconds. If you can make for a 50 hertz waveform, 10 millisecond to 20 milliseconds. So apply a gate pulse which is from 10 milliseconds of time to 20 milliseconds of time. Thereby you can keep this S1 and S4 alternatively switched on, and then you can get a positive and negative half cycles of phase A. Similarly, it's gonna be for all the phases. So let me quickly go to the discussion and then draw the circuit diagram for you, right? Draw the circuit diagram, draw the waveforms for you, right? Yes. It's not so easy to make these waveforms, but still I'll try my best so that my students who are actually having a little problem here, they would understand, right? Fine. This is the reference axis, y-axis. Fine. So I would take the gate pulses first. How many? 1, 2, 3, 4, 5, 6. Why did I take 6? Because I'll make the circuit here, right? A smaller circuit for you. So this is a circuit diagram. Again, I am making it here for our reference when we explain the working principle. Right. Phase A is coming out, phase B is coming out, and then phase C is coming out. Okay. Right. So what is this? This is S1, S3, S5, S4, S6, S2. So I need to give a triggering pulse to all the thyristors or all the transistors so that they can get on, and we can get a output voltage across the load. Okay, as I said, to have some output voltage you need to switch the switches. According to that switching, you will get the output voltage appearing across the load. So let me take this first one, like first pulse as Ig1, second pulse gate pulse as Ig2, third gate pulse as Ig3, fourth gate pulse as Ig4, and fifth gate pulse as Ig5 and Ig6. So what is this? All these are the gate pulses given to the switches. So for this I'm going to give a gate pulse of Ig1 similarly to all the switches. So what is the time, I mean the duration of each triggering pulse, or what is the switching instant of all three, of all 6 switches? So all that we're going to discuss now, right? Yeah, let me make it like this. See, I'm going to give a gate pulse from 0 degrees. Let's decide, divide this all into equivalent 180 degrees. So this is 180, 360. So this is 180. And this is, yeah. Yes. And this is my 360. Right. And this is my 90. This is my 270. Okay. Right. I'll make these angles on the top so that it will be easier for me to draw the waveforms, right? Fine. And this is going to be 90. Okay. This is going to be 90. And this is going to be 60. And this is going to be 120. Okay. And this is 150. And this is 240. And this is 300. And this is 330, right? This is the angle. I'm distributing or fixing the angles, or indicating the angles here. And one is only one, I think. Yeah. So this is how, yeah, the first triggering pulse I'm going to apply from, I'm going to take this black ink so that it will be visible to all of us. So I'll be keeping this, applying a gate pulse or a base current to transistor 1, switch 1, from 0 degrees to 180 degrees. Why? By turning on this from 0 to 180, I can get a positive output phase A, right? And I keep the gate pulse off here so that I can turn off the switch and I can end the positive half cycle there. Why? At 180, phase A, positive half cycle ends. So at 180, negative half cycle of phase A begins. So I should turn off S1 and turn on S4 from there. So to turn on S4, I apply a gate pulse here and then I keep that gate pulse on until 360. You got to note one point here, that I'm keeping this gate pulse on, base current on continuously from 0 to 180 degrees for S1, which means what? It is the base current which is persistently applied to the gate, base of the transistor. Thereby the transistor is on from 0 to 180. And at 180, I'm making it as like 0 amperes or 0 milliamperes so that the transistor opens, it gets switched off. So when it is off, then your positive half cycle of phase A ends. Okay, this is the idea, right? So why will I switch off the base current there at 180? Because I wanted to make my phase A to end at 180 degrees, right? Phase A's positive half cycle to end at 180 degrees. And at 180, I need to apply another triggering pulse to the base of S4, so that I can get a negative half cycle in my phase A. Okay, so that's how I'm keeping this on here. Until 360, the negative half cycle of phase A is required. So I keep S4 on from 182 until 360 so that I can get a complete negative half cycle for phase A. So gate pulse 1 and gate pulse 4 are applied to switch 1 and switch 4, with which I can fabricate what? VA. Okay, with S1 on, I can get positive VA, positive half cycle of VA, and with S4 on, I can get negative half cycle of VA. Similarly, I'm going to make the same idea, same stuff to the rest of the phases also. So coming to this VB, right? So VB will be obtained or fabricated from S3 to with the turn on and turn off of S3 and S6. So we have to turn on S3 and S6 alternatively, one after the other, not simultaneously, right? So what is that? 3 and 6. So 3 has to be turned on. Where you have to turn on 3? 3 has to be turned on at 120, because your phase B starts at 120, right? Phase B starts at 120. So we got to give a gate pulse, base current at 120 degrees, and till what time it extends? It extends 120 plus 180. So until 300, right? Until 300. So we got to give a gate pulse to the S3 switch from 120 to 300. Why? Because phase B output voltage, positive output voltage, what you are expecting in the output, what you are planning or deriving in the output, will stretch or will have its on time or its positive half cycle starting from 120 and finishing its positive half cycle until at an angle 300. So every half cycle will have a stretch of 180 degrees. Every half cycle will have a stretch of 180 degrees, whether it is a positive half cycle or a negative half cycle. So this is the gate, base current given to S3, sorry, it's not S3, it's S2. Okay, it's not, yeah, here I should give it. Yeah, this is the gate pulse which I am mentioning of. So we have to give a gate pulse to S3 switch from 120 to 300 degrees, right? And thereby your S3 will be on. But at 300, negative half cycle of phase B is to be derived in the output. So we have to switch off this S3 and turn on or apply gate pulse to S6, right? S6. So I apply gate pulse here at X6. Okay, and it extends. So only it is covering about 300 to 60. So as I said, every half cycle should be 180 degrees. So here only 60 is finished. So 120 degrees is still remaining. So you got to make this until this point, right? So by IG3 and IG6, you can turn on S3 and S6 alternatively, and you can fabricate VB. You can see alternatively, like when S3 is on, when gate pulse is applied to the base of the transistor, or when base current is applied to the base of the transistor, 3 S6 transistor is not applied any base current, so it's going to be off that time. That's how I am using alternatively. It is to be turned on. So what is remaining now? Phase C, right? Phase C. So phase C has to be fabricated from S5 and S2. S5 and S2, right? So we got to make phase C fabrication. So by turning on S5, I can get positive half cycle. So what is the instant at which the positive half cycle of phase C starts? It starts at 240, right? It starts at 240, right? So it is going to be starting at 240. So where is that? 5, right? 5, yeah, 5. This is the on time. Okay, so this is the time at which phase C positive starts. I need to turn on S5. So the switch S5 is gonna be on during that time, and it will be on for 180 degrees, right? Anytime if you wanted to have a 1/2 cycle, you have to keep that switch, concerning switch, on for 180 degrees so that you can get the complete half cycle. So now it is how many degrees is done here? 240 to 360, which means 120 is done. So 60 will be done here, right? This is the gate pulse applied to switch 5. So now the rest of the time you're going to make it to S2. S2. So this is how you're going to have the switching. So I'm going to put up some points in front of you. See what has decided the instance at which we have triggered the transistors, at which we have initiated the conduction of transistors. The instance, whether it is IG1 or IG2 or IG3, IG4, IG5, IG6, whatever it is, the starting points are not depending on our choice. So it is not our choice. So it is about the output voltage, which is demanding us to turn on the switch 1 at 0 degrees and turn it off at 180 degrees. Okay, if phase B, because phase B is starting at 120, you got to make S3 on at 120. Okay, so it is not we to decide at which point the switch is to be turned on. It is the output required voltage, phase angles, which decides this instance at which we are applying the triggering pulses to the basis of all transistors. Let's now go ahead, right? I'm going to make a voltage VAN waveform with its voltage calculation, and then I'm going to make VBN with its voltage calculation, and then I'm going to make VCN with its voltage calculation. Okay, so before I proceed further, let me draw this instance down, because I wanted to make all these phase voltages, right? Right. Remember a point here that I'm going to make a VAN, CN and BN, not line voltages. These are only the phase voltages. Okay, so as I mentioned here, the phases which are coming out, okay, right, how are they connected to the load? Let's see. The load is a three-phase load, right? Three-phase load. So this is your A, phase A. This is the neutral, so AN. So what is the voltage that is applied here? VAN, okay, and this is B. So what is the voltage applied here? VBN. What is the voltage applied here? VCN. So let me make a different circuit diagram here, because it is not so clear, I suppose. So let me make the circuit again. So this is your switch, right? Supply. So this is the phases that are coming out. So this is the three-phase A, B and C. Okay, this is the load. Three-phase load may be a three-phase induction motor. So three-phase induction motor has got a stator winding, which is three-phase distributed winding, and each phase will have its own resistance. So I'm mentioning that resistances here when I connect this inverter to control the speed of a three-phase induction motor. I got to connect this output of VSI, voltage source inverter, to the three-phase winding of stator of the induction motor. So induction motor stator has got three-phase windings, and then these resistance are this representation of resistances. What I'm going to make now are AN, RBN and RCN are the resistances of the three-phase winding of a induction motor. So what is the voltage that is going to be appearing here? I mean, it is going to be connected to this, right? So what is it? VA is connected, and this is going to be connected. This is going to be connected to VB, okay, and this is connected to VC. So this is this is C, right? This is fine, that's okay. So yeah, so VA is connected to the phase A of the stator winding, and VB is connected to the phase B of the stator winding, and VC is connected to the phase C of stator winding. So let's see how the output phase voltages are going to be appearing, right? So we have seen the switching sequence there, we have kept the gate pulses there already. So now we're going to see about how VAN, VBN, VCN are going to have its magnitudes, right? So to know that, let me take a period, I mean a duration during which I'll get the, I can figure out the output voltage 0 to 60 degrees, right? From 0 to 60 degrees, how many switches are on here? I mean, which switches are on here? If you can see clearly, it's S6, S5 and S1, right? S6, S5 and S1, right? That's fine. Okay, so S6 are I'll make that in sequence, okay? So it's gonna be 6, 5 and then 1, right? Is that okay? Fine. So how many switches are on? 6, 5 and 1. What is very 6? This is 6, right? This is your 6, this is your 5, sorry, this is your 6, this is your 2, this is 4, this is 1, this is 5, right? So which are going to be on now? 5 and 6 means 5, 6 and 1. Definitely, my dear, at any instant from 0 to 360 degrees, at any instant, you will find at least 3 thyristors or transistors on in conduction state. Definitely 3 will be there. There won't be a condition where you find only 2. There won't be a condition at a time where you find only 1, in on state. You will find all 3 on, definitely. Why? Because at all the instants of time, you have to make the fabrication of the output voltages, and the switching sequence is designed in such a way that the 3-phase output voltage can be obtained, can be derived to the output side at all the instants of the time. Am I right? So that's how you should not have any interruption. Phase A, B, C should have a value at any point of time from 0 to 360. So if you can see here in this case, I'm going to make a skeleton here. So which is on? S1 is on and this is off, right? So I'm going to touch this 4. So what is then? S5 is on. S5 is on. Okay, so there is something which is open, so I'm not going to touch it. And then what is on? S6 is on, so S6 is down. S6 is down, and the lower one here is off. Okay, this is how many are on now. So let me indicate that 1, 5 and 6 are on. And what about the output derivation to the load? This is about phase A. Phase A is gonna be here to the neutral, and this is your phase C, this is your phase B, right? And this is gonna be to phase B, right? So phase B is gonna be here, this one, and then phase C is this. So this is VAN. Why N? Because between this, right? Between this, and this is CN, and this is VBN. That's fine. Now, yeah. So 165. You have to be a little careful here, my dear. 165, right? So if one is turned, how many switches are turned on the upper side? 1 and 5. So let's say the circuit is going to be like this. The circuit is going to be like this. This is not working. Fine, that's okay. So let me take this circuit. So 1 is connected to phase A. Let's say, what is this? RA, what is this? RB, and what is this? RC, right? So that's what we have named there, RA and RB, whatever. So let me take RA only. Do not have a confusion between the different terminologies, right? So where is RA is connected to the neutral, right? So I take RA, and then another wire from the positive of the battery, another wire is connected to phase C, right? So this is RC. Am I right? So this is VC and this is VA. Are you with me, dear? And what about this? The negative is connected to only one switch is on to the negative side, right? So, and that is going to phase B. Phase B. What is this? Phase A. What is this? Neutral. This is negative. Are you with me, dear? So likewise, at every instance, you should be able to draw its skeleton. So from 0 to 60 degrees, S6, 5 and 1 are on. So when you make the skeleton and then derive the final circuit, it's going to be like this. So what is the supply here? Supply is VDC. Sorry if I'm making a smaller diagrams because I don't have much space on my board. So that's okay, right? So yeah, this is VB, right? So I have a supply voltage VDC, which is now distributed, given to three different phases, right? It has to be given to three different phases, something like one foot packet is being shared by three different people, okay? And it is connected in star. And when you make this switching, and you're going to get a resultant circuit like this. And now, what is VA? What is VB? Okay, what is VA? What is VB? VAN, VBN, and VCN. This is the observation now. So how to find VA, VAN, or VBN, whatever it is, to find that, so if there is VDC here, there will be certain amount of voltage dropped here in this, and the remaining is applied across phase B. Am I right? So first let me find what is VB. VB is equals to IB multiplied by RB. Am I right, my dear? What is IB? What is IB? What is IB? IB is nothing but the current that is flowing. The current that is flowing from the battery to the current that is flowing from the battery to the entire motor circuit, right? To the entire motor circuit, right? So to the three-phase winding. So IB is gonna be this. IB is the total voltage, what is there here, divided by the total resistance. So what is total resistance? How do you find total resistance here? So let me find that. So what is total resistance? It's a parallel combination of RA and RC plus RB, right? This is how it is. Am I right, my dear? So what is parallel combination? So it's going to be RA multiplied by RC divided by RA plus RB plus RB, something like that. So RA multiplied by RC divided by RA plus RC, right, plus RB, right. I'm going to take the same thing here. Same thing, my dear. So what is RT? What is RT here? Okay, what is RT? So RA RC divided by R A plus RC plus RB. So in a three-phase balanced winding, okay, of a three-phase induction motor, you have RA is equals to RB is equals to RC. In fact, all the impedances of three-phase is equal, right? So and it can be taken with a value of R ohms. So I'll substitute this R now. So RA is R multiplied RC is R divided by 2R plus R. So this is going to be R square by 2R plus R. So it's going to be 2R square divided by 2R. So it's going to be 3R square divided by 2R. So what is it now? 3R by 2. 3R by 3. What is this? RT. So I have to make this substituted into this, right? So I'm finding IB now, right? So now I'm going to take VB again. VB is equals to IB into RB. What is IB? Total voltage VDC divided by total resistance. What is it? 3R by 2 multiplied by RB. What is RB again? What is RB? It is again R, right? So R is going to be cancelling. So 2 by thirds VDC. 2 by thirds VDC. Is that okay, my dear? So now this is about VBN, right? This is about VBN. VBN or VB, whatever it is. So VBN, this voltage I am calculating now. Okay. So now what about VAN and VCN? VAN and VCN will be equal. That's known thing, right? VAN and VCN will be equal. But what is it? What is it, my dear? What is it? So if you can take a simple Kirchhoff's voltage law, you have VDC here, total voltage, and VDC is distributed here, right? So VDC, total voltage minus this voltage, is going to be the voltage across this, right? So VAN or VCN, whatever it is, VDC minus 2 VDC by 3. So it's going to be VDC by 3. Very good. So what is that finally you're going to get? So VAN and VCN, right? VCN, both are equal to VDC by 3. So what is the voltage here? What is the voltage here you're drawing? I mean, you have deduced from that. It's going to be, VDC by 3 across this. And here, what is the voltage here? 2 VDC by 3. Is that okay, my dear? It's not a simple stuff to do, but still we could manage. Right. So VAN, VCN have got the same value, which is VDC by 3, and VBN is 2 VDC by 3. So what did you understand out of this, right? So this gives us a very clear picture that out of the supply voltage, the voltage is being distributed in the proportion of 1/3, and the remaining is 2/3. So 2/3 is across this single resistor, and 1/3 is across the parallel combination of RA and RC. So what is the voltage across VA now? It is plus or minus. It's going to be plus, right? Because it is connected to the positive. And what is the voltage across VB? It's minus. So you will get a positive voltage, and for this VA and VC is going to be positives, and VB is going to be negative. Am I right, my dear? So positive VDC. So I'll indicate here also. So positive, this is negative, this is positive. So positive VDC by 3. So let me indicate the values here, right? Let me indicate the values here. This is VDC by 3. Okay, right? I don't have a space here, that's fine. So VDC by 3, and this is 2 VDC by 3, and here this is minus VDC by 3, and this is here minus 2 VDC by 3, right? If I can make like that, so see, this is plus VDC by 3, and and what about VB? VB also I should indicate the values here, right? So this is let's say positive side, plus 2 VDC by 3, and this is plus VDC by 3, minus VDC by 3, minus VDC by 3, and this is minus 2 VDC by 3, and here also I can indicate like plus VDC by 3, right? And then this is plus 2 VDC by 3, okay? And this is minus VDC by 3, and this is minus 2 VDC by 3. Let's see how it's going to be now. See, so from 0 to 60, what do you got here? VAN, VBN are positive VDC. So positive VDC, positive VCN. Where is VCN? VCN is positive VDC, right? That's fine. Okay. And what about VBN? VBN is minus 2 VBN, right? This is VBN. Minus 2. Okay, and if you can find in a similar way for the instant of 0 to 120, and if you can see the switches from 60 to 120, the switches which are going to be on from 60 to 120, what are on? S1 is on, S2 is on, and then S6 is on. So you will get S6, S1, and then S2. So 5 is gone. In the place of 5 you got 2. So if you can make the similar analysis, then you will get VDC, VA is going to be plus 2 VDC by 3, and VB is gonna be minus VDC by 3, and VC is gonna be minus VDC by 3. Okay, and then if you can see it from even 120 to 180, you will get the similar analysis like this. Similar, I mean, you'll get a plus VDC by 3. And what about VB? You'll get a plus V. This is VDC, right? Right, that's it, right? And you'll get a negative VDC here, and then, right? And then from 180 to 240 for another 60 degrees, if you can see, you will get this as minus VDC by 3, and this is gonna be plus 2 VDC by 3, and this is gonna be plus VDC by 3. What is this? VCN. That's how for every 60 degrees you have to evaluate and find the expected, or the output voltage. Okay, the output voltage of all the phases. So, and then from 240 to 300, 240 to not 300, yeah, how much it's gonna be? Plus 60, right? That's 300. So you're going to get a minus 2 VDC by 3, and then it is going to be filled finally. Now this is going to be like this, right? If you plot it, you're going to get like this, my dear. Fine. Is that okay? See, phase A is starting at, I'm going to make it a little more interesting for you. See, phase A is starting at 0, right? 0 degrees, and then it is finishing its positive half cycle where? At 180, see? And it is starting its negative half cycle and then finishing it at where? 360. So one full cycle of phase A is achieved, right? Now what phase B, right? Phase B. So phase B has started its journey at 120, am I right? Positive half cycle, and then finished at 300, am I right, my dear? And then it started its negative cycle here with one step, and the second step is going to be, it should take up here. So that is taken here. So it is taking to minus 2 VDC by 3 and then getting down. Right, and coming to VCN, it also has its positive half cycle started at 240, right? According to the standards of the what we have, phase is to start at 240, so it is starting at 240, and then it is continuing its rest of the cycle here, and then this is a negative half cycle. So this is how you have phase B, okay, and phase C. Is that okay, my dear? So this is how it's gonna be. And yeah, and last and but not the least, you should make this also, if it is there for you, for your knowledge. So this is only about phases. So if you want to take line voltages, VAB, so VA minus VB, which means you have to subtract VA and VB. Suppose if you subtract here in this 0 to 60 degrees, plus 2 VDC, plus VDC by 3. What is VB here? What is VB here? Minus, right? So minus of minus 2 VDC by 3. So what you'll get here? So it's going to be, yeah, it's going to be VDC plus. Are you understanding, my dear? So you'll get only VDC if it is a line voltage. Likewise, you can find for VBC line and then VCA line. VBC line is VB minus VC and VCA line is VC minus VA. If you can do this, it will be very nice. You'll be so happy to understand this kind of stuff. So this is about a huge topic. I think it took more than 1 hour. So have a nice time. See you next time.